Yeah. Uh, Everyone can hear me, right? Okay. Yeah, a very warm welcome to you all for today's colloquium. We have a distinguished Professor Souradeep from RRI. He's the director of Raman Research Institute, Bangalore. So let me briefly introduce the speaker. He has done his PhD from Ayuka, Pune in 1995. After that, he did it Canadian Institute for Theoretical Astronomy and later at Kansas University. In 1999, he joined Ayuka Pune at Ayuka Pune as a faculty in various levels till 2019. Uh, 2019 to 2022, he was a professor at IISER Pune, so he is not new to the IISER system. So he was the chair professor of Department of Physics at IISER Pune. In 2022, he has moved to RRI. He took up the position of director there as a director currently. So he is his research expertise is in gravitational astronomy. Mainly, he is leading the observational cosmological part from India for the with the LIGO India collaboration and CMB Bharat. So he'll be mainly talking about the CMB Bharat initiatives in India and several accomplishments in his career. I don't want to list out everything, but which includes some of them. The prestigious Gruber Cosmology Prize in 2016 and Breakthrough Prize in Fundamental Physics in 2016, Swarna Jayanti Fellowship, DST, and several of them. So he is a fellow of Indian Academy of Sciences as well as the fellow of International Society on General Relativity and Gravitation stuff. So you can go through his profile. It's a very interesting profile. So first, I welcome Professor Tarun Souradeep for the colloquium. And yeah, so for accepting our invitation, coming here.
Okay, so let me begin by thanking IISER Tirupati for the invitation to give a talk to students. I love doing that over the last decade and a half, or no, 2 decades. I've been to do that, and I'll tell you the reason for that. But let me thank also Jesse for a very generous introduction and nice hospitality here, and Arunima. Oh, there she is. And so you have wonderful faculty in this field, and I hope this grows much more in Tirupati. To why I think that would happen naturally, because many of the milestone questions in science, if you hear big people give talks, what are the burning questions of the universe? So I have heard very leading people give that. In their list of 10, 6 of them or 5 of them at least would be cosmology and gravitation, black holes and information loss. Okay, these are questions that are challenging us all the time, right? So to me, I think the way science proceeds, this is my own personal view, and you should think about it, but I'm happy to discuss, is that there's a cycle of quest and conquest. It's been going on for ages. Now, if you think of it, even if Galileo wanted to see the Jupiter and its moons clearly to understand dynamics that led to, the system, he would have needed a good enough telescope. See, I doubt that it's not just Galileo who thought about it, that it would be good to look at good resolution, but he probably also had the right lens maker at hand who made the best lenses of those times and got him a telescope. Similar story goes on to other things where you have questions that need to be answered, pressing questions, and then you realize that trying to answer them with experimental verification requires you to develop. So Tirupati is blessed to have IISER and IIT right next to us. To me, I have never seen them as different. So one part of my CV which I always talk about is I'm an engineer who moved to physics, right? So these two things it's essentially at some level the best experimental physicists are excellent engineers. Lot of engineers at the top of their field understand physics well. They may not talk in terms the same language, but they do that. Okay, so I many of you may know that I was involved with the LIGO India project, which is well underway. So it's under construction. So there's a company awarded the tender. So talking about the next exciting thing that I hope to have many of you join up is the next thing in gravitational waves. And this is just not me, but if you listen to the Nobel Prize lectures of Kip Thorne, otherwise it's easy to Google and find that. You'll see both talk about the next big milestone, and that's the detection of gravitational waves from the beginning of the universe. Okay, and so to me that's a quest. Okay, and then I'll tell you how we go on to conquer it and why we think that's a absolutely pressing to answer. Okay, I hope to convince you of that. Okay, so let's start with gravitational itself. Okay, so 1916, Einstein something called the general theory of relativity, extending special theory of relativity that only included uh, gravitation. So you didn't need to postulate a force. Okay, and that led to even physicists trying for all other interactions. But this is extremely beautiful. It's rooted in very beautiful mathematics, which appeals to a lot of people. But that's not enough for a physical theory. What really makes it stand out is that it's been extremely successful. All kinds of tests that have been thrown at it till now have really been precision tests which have really been passed by Einstein's gravitation. So we do know Einstein's gravitation quantitatively gives better predictions. Okay, now so much so that your GPS uses corrections based on GR to make sure that you can get to a meter. If you don't have those corrections, you'll be off by hundreds of meters. So, I mean, so imagine the importance of this, right? And to me, this famous and successful theory has three milestones, absolutely milestones that describe it. Einstein's first ability to build a model of the universe. Okay, think about it. Newton's theory, Newton himself knew that if you have a uniform distribution of particles, which is a good guess for the simple model of the universe, that's inherent. It would collapse, right? And collapse exponentially. Collapse exponentially. So that doesn't look like a good model, right? Where everything clumps up. Okay, but Einstein's gravitation gave you a way out of it. Added dynamic aspect of space. The first time you saw space time is not only a thing carrying the information about matter distribution curvature, but also it's dynamically changing to accommodate movement of matter. And that is our expanding universe model. This was to the extent that even Einstein tried to stop the universe from expanding by postulating that there was some delicate balance and all that. Second thing I won't talk about, I won't talk about at all, are black holes. Black holes are absolutely enigmatic objects. They are a mathematical construct. Okay, it just seems to be very strange. Singular points of physics are shrouded by a surface where information flow in but cannot flow out, right? These are black holes. So it's a one-way membrane. And that was something that has spurred a lot of intellectual activity in the physics community. I mean, what happens to the information? Does it all kinds of things? And third are gravitational waves. Now, why are they key? Because While Einstein's gravitation, as I said, I use the word quantitatively outdoes Newton's theory in even day-to-day circumstances. GPS won't work without that. But quantitative, so you could imagine some smart person, thinking of gravitation by some extra terms and trying to fit everything. That for a long time. I'm not saying it's easy to do that, but in principle you can think of it. But once you have detected gravitational waves, you just cannot have Newton. Theory of gravitation has no space for propagating modes. This has immense implications also in this field of particle physics because and quantum science. I mean, quantum field theory with fields that have a radiative degree of freedom. And this 2016 discovery showed you that gravitation, as we understand it in Einstein's theory, does have this freedom, and that is why this was heralded as a huge thing. Similarly, modern cosmology. So, what has happened till since 2016? Of course, there are 4 windows that we are now aware of in which we will start measuring gravitational waves. We have already opened one window in 20, which is something like 10 to 2000 um, hertz, right? So, this is comparable to our audio thing. So, a lot of this language of hearing gravitational waves. All of you are smart enough to realize you don't actually hear a sound wave. I mean, gravitational waves first, and also cannot sound waves don't travel in space. Okay, they need a medium. And very recently, 2023, they may have heard seems to be strong evidence that radio observatories, which are as clocks in the sky, saw some jitter which they could attribute to gravitational waves. Okay, this is yet to be a discovery because you need it's somewhere between 2 to 3 point some sigma, depending on groups. But this surely will come up, and with square kilometer array, which India is part of, it will again come up. Okay, and all through, I'll tell you how exciting it is to be in science in India now, because we are part of major initiatives. So, Square India is a partner. LIGO India is coming up for the first window, and GMRT and other upgraded GMRT and other facilities which have been will and help with the radio pulsar thing, timing thing. Then there's one experiment that will go up in 35 time scale. It's European Space Agency, which is sending up, which will fly in constellation to measure gravitational waves. All of these not only have great astrophysical significance, it's going to be a new way to understand the universe, but at a great level also cosmological significance, because with as you see this mergers far away and things like that, you can start measuring the expansion of like that. But the thing I'll talk about today is this next quest, which is very close to my heart because I work in the cosmos background. And our best bet at this time, gravitational waves right from the beginning of the universe, lies in better of the cosmos background, much better than the extremely good we have now. So it's a field which is struggling against its own success, because for 3 days, as I'll show you, things have gone very well, and people are asking, and we do think we need more. Okay, so let's give you some flavor of cosmology in the sense that you should be told. So why do we do cosmology? I have a simple answer. I mean, why wouldn't you? You were a human on Earth and looked up to the sky, you don't see it, but you do, right? But it's spectacular. Obviously, ask what is out there, right? What is our place in this? And we know that these stars are all just a part of one galaxy. They are similar worlds billions of them which we have measured. Okay, so if you zoom in, you see galaxies all the way, right? Right from a time when they were just formed, because light takes that much time to come. Okay, so galaxies which are just being formed, they are, many, many galaxies, 10,000 probably in this picture. Okay, a galaxy, again, I tell you, is not a trivial object, but for cosmology, point particle. So for us, we only think of it as a space-time dynamics, right? Just like if I were to look and I use dust particles and shine a light and monitor their movement, I won't really bother about whether the dust particle is made of what material. Similarly, but I should point out that this is a massive system. I don't know how many of you know, but just 3.26 light years. So this is, it takes thousands of years to go across, 10,000s and 100,000s of years to go across a galaxy. Massive system, it has its own dynamics. People spend their entire lifetimes working on such things. You have someone here who does that, has been doing that. So Arunima, so this, all this being relegated to a point particle may not, appeal to, but it is what it is, and all unimaginably different. Okay, okay. So now simulation of the universe, but we have actual data which is almost as good. So this is the distribution of galaxies in our universe, right? And if you see, if you are flying through it, you can see that galaxies are not distributed uniformly. Okay, they seem to have very well defined structure. So physicist, you would be already starting to study that immediately, right? Luckily, when we started to build our first model of cosmology, we hardly had much observations beyond distance, so we didn't know this. So we used the simplest ideas, and it so happens that these guys were so smart that they thought in the right way. So one of the things you would see is a data set from 1970. 1970, if you projected all the galaxies back onto the sky, you see particular direction crying out for attention. There is some graininess, there is some patchiness. Not as if I can say, oh, there is something interesting happening in the universe. Over such scales like this, and if you are blessed with glasses like me, take them off and you will see two nice white patches. Okay. Parts that are cut out, this is north hemisphere, this is southern hemisphere. Those days we are not very good at peering through the galaxy. Nowadays there are, better observations. But that is what I'll start with as a zeroth order in the universe. The matter is distributed isotropically around us. It's the same in every direction. Okay, then a simple maths theorem. I mean, it's quite profound that a medium at each point has to be homogeneous. Okay, the opposite doesn't. You can think of that also, and put it into the equations of general relativity. Uh, spews out a surprise that, as I said, even stumped Einstein. Told you that there can't be any universe that is just sitting. It either has to be expanding or contracting. And then Hubble peered out and showed expanding universe. Okay, so this is all in a nutshell. Someone somewhere would be teaching you this. Very simple. I mean, what I'm saying is that is the strength of physics. We are able to abstract out all the problems that we solved in Resnick and Halliday. If that is still the book you do, uh, you drop friction, you drop this because you want to get to the essential point that you want to establish. So if you do that in cosmology, you have a very nice model, simple model. Okay, and basically we imagine as the universe is expanding, okay, the matter would be denser in the past. If there was radiation, it would be hot. So it's a hotter and denser universe in the past, and up to this point, somewhere here, not second, but even 10 to a minus 16 seconds or something, lab tested physics to say what such a universe would do. Look out and see, do we see it happening, right? And that's what the game has been. What I wanted to emphasize is the underlying model is simple. I also wanted to tell you the power of that. I mean, and somehow, we moved along the same line, but this is obvious that you have hydrogen and helium at some ratio 75-25 maybe, and then at higher temperatures it becomes a plasma, so you can't observations beyond this point, and we see essentially a surface of plasma surface around us. Okay, so it's again a remarkable thing that nature has been very kind, that around every curve of the universe, particularly us, there's essentially IMAX which is placed at about 43, which is a plasma screen. So, this maybe 20 years back you couldn't say that, but nowadays plasma screens are something you. So, it's a plasma screen. 1965, when it was first detected, to 92, this screen was basically, we didn't see any picture on it. So, basically, the contrast was so poor, our contrast of the images were so poor that we couldn't see anything. That would have been very boring, but actually people really made a lot of things out of that. But uh, we started seeing structures. We could see some areas of the sky were little hotter at 10 parts per million. So it had to be built up, and that again is a conquest. It took 25 years. It was expected because we see the galaxy distribution is not uniform. So the of the same inhomogeneity in the radiation, because radiation and matter coupled in the past, and that has to be there. This is, so we expect it took us time, 25 years to see them. Okay, and then the field really took off because now we had basically of okay, so this is showing you the Kobe satellite, this first discovery of fluctuations on it. It all measured this plasma screen uh, distribution of photons and found no deviations from a perfect black body, known black body, natural black body, period. The stars here are blown up by a factor of 400 to for you to see them, right? So this is spectacular. So this thing uh, the fact that it's a black body tells you that the universe, as I said, has expanding from a hotter phase. Now that is something that you would know. How do we know? This is a absolutely unquestioned answer. If it didn't happen, you can't create a black body because the temperature go up to a point where photon non-conserving processes have to happen. Okay, just thermalizing photons is not going to give you a black body. It will give you a photons are bosons. So what's the distribution it will give? For Bose-Einstein statistics. But Bose-Einstein statistics are there, right? Or I don't know what you call it. The chemical potential. The chemical potential when there is no conservation. Total number conserved, then you have a. So the fact that we measure mu to be 0 to a minus 5 level till now means that it is in processes where, so the universe must have allowed that. So universe must have been at 10 million Kelvin. Now it's 3 Kelvin, but it was million times hotter. Okay, then we saw this picture that told it allowed us to connect these fluctuations in the universe to the fluctuations that matter distribution, the galaxy distribution that we, right? The lumpiness that we see, we believe the seeds lumpiness was sowed at this time. So this is a universe which is 500,000 years old now here, and in years, if you let Newton's, this thing, gravitation has this instability. it is not totally taken away by Einstein's theory. It is tempered in a from a potential to a power law when you have an expanding universe. Okay, so you can controlled enough with the right expansion history to start with that we have measured here and get you the galaxy distributions that we do here, and that has been a remarkable success in the last 30 years. Okay, actually opens the door to the big question. So I am seeing a plasma in fluctuations and I am inferring everything about the universe based on this connection, right? But who who kind of created those? Why was the plasma perturbed at all? And it has physics which we don't really know. So this is sort of running through history happened. So this is the Kobe discovery. Interestingly, this entire career of mine. So I started my PhD in 1990, and so we had the then the next decade was Wilkinson microwave anisotropic probe, which was a NASA, which was kind of much better than Kobe. You can see the fluctuation at more well resolved. And then Planck is the best that we have in the next decade. And this is big question. What next? And there are a lot of ground experiments. So we know these three all the time, largely because they are the real, game. Many of the amazing discoveries were made by ground, like the first polarization measurement was done by ground experiments. Okay, is this game going to go further, at least in the space world? So that is asking. Now, why would you want to do that? In the last 30, whatever, 35 years? No, 1990 to now. Uh, these numbers that we have. So I told you that I know the initial fluctuations, I know both are measured. I know the process, and the process, how tempered is gravitational collapse, depends on what is the content of the universe. Ionic matter I have, how much of cold dark matter I have. I to be zero if I was a true bred thing, because I don't have any idea of what is the right candidate for it at this time. But it happens in not something in my hand. And if you do all that, you also find that there is a non-gravitating matter content, which is the largest. It's 70%. That other thing is about 20% and 25%, and the 5% is matter which you have actually experienced in our lab. So it's very humbling. So one should always keep in mind that to me, cosmology is just starting. It is something not to take as a Bible. I mean, often I find physicists treat it like a particle data group kind of a thing. I would, because it's built on a very simple holistic model, right? We could be totally off, right? That's a possibility, and that's what is exciting. Very good observations. You can think broadly, but it's not. Now, in my experience, many of my friends, extremely talented guys, have thought of new this, and you usually hit something or the other which rules you out. So it's a tough game, but that's what we want. We want a tough, simple one. But this is cosmology now, okay? And visual representation of how much has happened even in my career, right? All these error bars of uncertainties. Oh, not my career, sorry, my faculty career. So 2020, 2000 onwards to now. This is the shrinkage. In my time, parameters were not known to a factor of 2 when I started research. Okay, through that to get percent thing. There are other ways to measure it. Ask, how much information have we gained, and that is basically the inverse of the area in your model, and that's called a figure of merit.
Parameters get from all the theoretical comparisons or how?
Parameters we get by, for these parameters, I know what to predict. Okay, I do not the exact pattern, but the power spectrum, and
You have observation?
I have model, and I can do a Markov-Chain Monte Carlo to move all the parameters simultaneously, you know, and then I'll get these, you know, things. I mean, this is a game has been played by physicists also. So you see this figure of merit relative to Cope is at least a 10 billion in the estimate, and it could be some 4 orders or 5 orders of magnitude more for bigger models. So this is interestingly, oh, something, but this is 3 times faster than Moore's law. Okay, you've already, how many of you know Moore's law? This is the rate at which computing ability has been grown. Okay, so this is grown 3 times faster than that. And these are from our final paper of Planck, which we are part of in 2018, where we made that point that this thing. So it's been an extremely successful story in pinning down a very simple model. But then simplicity of the model, and then we also have established some of the underlying paradigms, right? You know, this model that we had a hot dense universe. This is a good thing, but we can work further on it to make sure we have, you know, right to a greater extent. Then you can ask, you know, I said that the universe is isotropic. Is there, you know, something wrong? Then I told you the fluctuations here. I didn't tell you that, but the CMB fluctuations are generated by very basic component physics. So a plasma which is perturbed, you can work out the equations. And the interesting thing is everything is physics that you've already learned, but you have to learn to do it in an expanding coordinates. That's all. Okay, and that has its features of damping and stiff stuff like that. But you know, in terms of physics, it's but in expanding coordinates because your universe is expanding physically. Structure formation, we have good evidence now, even beyond the CMB, to say that, you know, yes, there were tinier fluctuations before, and then the structures have been getting better stability. The biggest question is, what do we want the initial fluctuations to be, right? The ones which were generated right even at the other end of the plasma. And that is something that I think is a big unknowns. Okay, I should tell you the interesting thing is we have a simple model and quote numbers to a percent accuracy, but you know, we have 90% of the universe is made up of things that we don't know. Seen them, I haven't identified them. We don't know what the cold dark matter is. We know something like that exists because, you know, otherwise you can't see, right, with what you observe and this thing. So you see light bending by an amount. This is seen to n sigmas, like, you know, there's no doubt about the observational thing. Now it think, okay, is there something which can give that without putting cold dark matter? And people have tried. I mean, people are still trying. Then you have a cosmological constant, which is, you know, really, really worrisome. So I remember when I started my PhD, and, uh, maybe many of you know him. So I had gone up to him and said, what do I work on in cosmology? He said, oh, there's this cosmological constant problem. And even at that, was like people had spent decades and gotten nowhere. I wisely not, I mean, not what I'm going to work on. But there is a problem. I mean, even if small cosmological constant problem, we have the problem of how to make it zero. So now we've forgotten that original problem which was relevant in the 70s and 80s, and you know, constant in different light. Okay, but I'll that there has to be ultra high energy physics beyond your physicists who are here, which has to be there if cosmology has a consistent picture. We have to see evidence for that. What kind, what is happening, you know. So that is the thing. And so, as I said, so if you look at the evolution of the universe, sometime thing happened, which we don't know, it's in the quantum realm. And then we have this evolved universe, which is 14 billion years old. We have a wonderful screen in which this played out, right? The past universe here. And our guess, as I said, between these two, we got all the constraints on the cosmological model, and great. Our best bet for the initial fluctuations is also quite exotic. Quantum fluctuations. Now, in these days of quantum mission, what can be more exotic that anything and everything that you see as a structure in the universe arose from a quantum fluctuation, right? So that is our best bet is. It's called inflation, and until we really see reasons not to have it, it's there. At this point, observations check out almost all the predictions of a simple inflationary model. It's remarkable. So I won't go. It is the way we get a homogeneous isotopic universe. Why inflation came into being. It naturally stretches out such that even if it has curvatures, it gets ironed out. So it's a geometrically flat universe. We have verified that to high accuracy. The perturbations in inflation, they are supposed to have same fluctuations at different scales. We have checked that. We have spin characteristics. So we have this density perturbations, and what are, so inflation can generate density perturbations, and we believe we are seeing the results in the microwave background as well as in the galaxies. These all arose from of inflation, okay, generated. And then there are other aspects. There are no entropy fluctuations typically in inflationary models, simple inflation. We have checked that. I mean, we can't account more than 5% of entropy fluctuations there. So these are getting, and the underlying statistics Gaussian, because quantum functions in a weakly coupled field are naturally Gaussian, which is what everyone now talks about. This is just a snapshot from the Planck 2018 paper, telling you numbers that all that I stated are new number. There are numbers associated with how that, and we can keep improving that. I mean, that is fine. But the biggest question is, any model of inflation that generates these density perturbations must generate gravitational waves. Okay, this is inescapable. Okay, so we should look for them. If we think inflation is a prediction that at some level you will see gravitational waves, you see that would be a huge plus for the early universe scenario that we are painting. And this is showing density perturbations. They imprint it as density perturbations as scalar perturbations. They just compress or rarefy. They can't do anything else. And so you see intensity fluctuations, but gravitational waves can actually tamper with the linear polarization of the field, okay, of the CMB photons. And they can be by measuring the CMB polarization very well. Okay. To me, this is like a must do thing. So because each polarization of gravitational wave, which is like a graviton because it's of quantum origin, like a minimally coupled scalar field. Again, this is for people who understand it. And the generation of scalar perturbations has to be accompanied by perturbations. What is uncertain is the ratio of the two, because different give you different ratios. Till now, we have checked that the amplitude of gravitational waves is about less than 3% density perturbations, but we can go to 10 to a minus, right, with the current technology, and that's what we should do. So this is the search for gravitational waves, and just a little bit of historical thing, because thing I got into as one of the earliest projects I worked in, and this school of Alexis Saravinsky, which was involved. So this Alexis Saravinsky, his student Varun Sahni, his student Tarun, and my first student Amir Hajian, sitting here. was the first to tell that inflation will generate gravitational waves. I won't go into details, but it's amazing how much ahead of the curve. Okay, and that gravitational wave is seen at cosmological scales, and which is where we detect it first. But for future generations, remember that if that is inflationary gravitational waves, you can see it up to million scales. These are far, far higher frequencies than LIGO is probing. So you would need other detectors, and all through LISA, better LISA will see it, better phase will see it. So this is something that is unique about this, that it's a prediction. If once we see it here, exact almost this prediction for where we should see it in our hands. Again, they will be, that will be a quest, and we don't have currently the technology to solve them immediately. Okay, so I'll just skip this. This is, the predictions of the first CMB normalized gravitational wave power spectrums that I a part of my paper in 92 and in my thesis. You see at that time do much better than what it is doing to do now, and then we have been doing this game of so how do I detect gravitational waves? So density perturbations create temperature, intensity variations because waves on the plasma surface, and also there's a component that if the radial velocity of the plasma is towards us, it will be blue shifted, hotter, appear hotter, and if it is moving away from us. So these are the two things we can see intensity of the microwave background. Okay. But in the polarization, you can see the velocity field, and a part of that velocity, I don't know how many of you have done fluid mechanics, but typically potentials are curl free, right? So we have measured the curl free part of the polarization fluctuation. The curl part cannot be generated by density perturbations. Okay, the only way to generate them is gravitational waves, because gravitational waves can shear. I told you perturbations can only compress. So if you imagine a box, or rarefy, stretch in one direction, stretch in other direction, whatever, but it cannot do change that square box to a rhombus, right? It's shear. So if you have density perturbation, it will give you. If you had gravitational waves, you would the plasma surface will be warped in a particular way, and that we can detect. So this is the CMB sky, which we have measured extremely well. This is a ocean temperature map, just to emphasize that there is this polarization pattern. The polarization pattern, if there are gravitational waves, have handed distribution. So you can see this wall, if I take its mirror image, it will look right. It's got a direction to it. So we are looking for such patterns in the polarization. Haven't seen it yet, but that's the search. Okay, so these are telltale signatures of gravity, and we believe that we can search for them up to a very high accuracy. So remember that number. This time it's 0.03. We can go to 10 to the minus 4, 3 orders of magnitude higher. And so for that, as I said, we have learned a lot. This is the power fluctuation power spectrum. And asked me how do we get the models. A model predicts these fluctuations, and we measure them, and we have measured things so well that this I mean, things can't get better than this, even if we launch many satellites later. This one is known fairly well, but this one is not known at all. So we definitely need another space, and that's the main thing I wanted to point out, that we are next generation CMB experiment. Okay, and why space? Now, I told you there are a lot of based observations, but from the ground you can only see parts of this spectrum in to say 600 gigahertz. There are only few things that open up, and in sky we can see all of it in space. And we don't have atmosphere to deal with, we don't have thermal variations to deal with, will go well. So the story is that we group Cosmology Consortium, very much like the LIGO India project. We had a Indigo, which was experimentalist and scientist consortium. We have a consortium of cosmologists of both kind. We proposed to ISRO a satellite fairly big, but not enormous. Not, you know, it's something that fits into GSLV Mark III, and it has to be launched to the second Lagrange point, where it will quietly sit and keep. What sits in it are much more improved vectors than what flew in Planck. Okay, and they are available because they have been deployed. So the whole idea is to get everything together and put it into space. This is various people involved, and to us, it's extremely, at the one thing is to look for primordial gravitational waves of the universe. But if not, the CMB has done so much for you. I told times Moore's law, and we know 90% of the polarization is yet to be tapped. Okay, so we should just do it. We have the technical capability to launch a satellite to do it, and that is what we aim to do. There's a chance that we will see gravitational waves, and these will be different from the LIGO success because these are going to be classical. They are going to be of quantum origin, and then we will have folds improvement, another billion folds improvement in understanding various things. Model neutrino physics, we will, constrain it to an extent, total mass to an extent that we can distinguish between the two hierarchy possible, inverted and mass gaps. And then of course expected discovery space. I'll just skip over this. So what I like about this is just project, it involves everyone. Okay, so it has of course path-breaking science. I mean, if it happens, great, and very high value science also. Slightly bigger community and possibility, and then there's a lot of. I mean, you have this amazing natural thing which is a plasma screen on which the universe is written script, and we are just taking out all the information possible. So it's and it will also naturally give you a lot of legacy value things for galactic physics and all kinds of things, and so it has a breadth as well as very high this thing. On the technology side, there'll be things that India has to prepare for. Any satellite to L2, but it has gone to L1, and there, why not L2? There are many things. Every part of a big project that you can think of, colleagues in these big experiments they are. I mean, it involves people doing data science, to AI, to this and that. So I can't tell you who amongst a bunch of you work in it. I mean, almost everyone will have some role to play, if at all, right? So this is a picture of the schematics of this. I won't really spend time on that. Me. So we have multiple frequencies. It's a fairly complex thing, but it's not undoable. I mean, we have sent similar satellites before, and this with a much better tech. It's improved technology. Absolutely fantastic. So what's happening in the country? In my own institute, there's a faculty who is. These are detectors are cryogenic, so they work at millikelvins. So we are going to cryogenic detector. At this point, there is some lab which is going to colder and colder electronics and colder detections. Okay, the antennas you can design. Uh, this is, but for CMB you may have to design it at this size. These are etched onto wafers, and then these are being tested, and various additional things of amplifier at a very cold temperature. These things are happening in our lab. Also deployed this system so you can go to exciting places. If mountaineer or excited about mountains, this is in Hanley. So tested and various other places. I'll skip this. Then we have a high altitude site for astronomy where the is 2-meter telescope sits. BARC's DAE's MACE telescope, gamma ray telescope sits. That area is also high and dry and very experiments. Not as ideal as going to space, but we are also look at the ability to set up telescopes there. In that direction, we are doing site search in Hanley. So, people are going, deploying precipitable water vapor. We want to know how much precipitable water, okay, and then compare it along. And we have very good sites marked out. We will be following them up and identifying something. Then ISRO is also setting up a telescope at similar frequency. Science is not CMB science, but they are setting up a 6-meter dish in this band, and they're building the receivers which are very similar to, right. So ISRO at Space Application Center, these are pictures from center, which shows you there's a basic design. Some of it has been already fabricated. There's a site identified, may not be the best one for us, but exciting things are happening. These are really the kind of things that sit with detectors. But if you think is you don't want to do science, this is what sits in the best satellites, where we are still behind, right? And these are all developed at Space Application Center, and some of this will again happen in Research Institute and other institutes. Okay, so there's some demonstration things. I won't get into that. So I will leave you with this message. So the last of a CMB space mission was in 2009. Okay, and we have, and we are as a community seeking a next generation CMB. And I feel that India taking kind of a big lead or moving forward at this time would be great, because both Europe and US have limitations at this time on all fronts. So I think it's a good time. We have really a mature space program, mature education system, and uh, the story. That's what I wanted to tell you. So welcome to the next thing.
Professor Souradeep, for the exciting talk. We got an idea India is leading to in the next decade also. Before moving the session, as a token of appreciation, we like to present. So I welcome Arunima, our chair, to present the memento.
Thank you. Oh, okay, wonderful. Thank you so much. Okay, thank you so much for the invitation again.
Yeah, so if you have questions, please feel free to ask now. Yeah.
Okay, so cosmic microwave background has polarization, but the polarization that we meant, it might as well be coming from dust and magnetic fields in the foreground sources.
Yeah.
So how do we isolate the impact from the CMB and also from?
So are you a undergraduate or a PhD student?
I'm doing my 5th year here. master's thesis.
Okay, so this is one of the biggest challenges we have in the field. Reasons this is stalled is because we need to remove these contamination at a very high level. Okay, but we are capable of that. Okay, so we have these studies which show that what you do is, okay, basically what happens is the background fluctuations are fluctuations in the black body, and if there are no entropy perturbations, in thermodynamic units, it is the same fluctuations would remain the same across frequencies. Now, if I measure the same fluctuations at different frequencies, the component that's cast and other things changes. Remove that part by modeling out the part changed. Okay, so that's the game. Now, this is a game which is played colleagues, but notably Tuhin Ghosh and then Somen Basak. Sir, Somen Basak is in ISA Trivandrum, and then many, in ISA Bhopal. So this is an BHU. So multiple groups in India and of course all over the world. This is a challenge, but we have good control on it.
One more similar question. How do we know that? Okay, you mentioned that we are seeing curl on the polarization field. How do we know that that could just not be of a projection of a 3D field onto a 2D surface? Because all our observations by design are 2D.
No, but the polarization is basically in that is traveling to us is in the plane. So the polarization is not a projection effect, right? It's a light traveling to me along the z-axis. So the polarization of light is always transverse, right? So it is necessarily a 2D vector. It's just that on the sky you have curved sky and there's little more mathematics then. But typically if any light coming to me, the polarization is always in the plane perpendicular to the propagation. So if it's coming, then the polarization is on a screen. Yeah.
There is one more mic thing. Okay, my question is my question is signal from the quantum fluctuations that is stochastic. I mean that is stochastic, and the reason is we have a this quantum fluctuations, and so it would have a quadrupole moment.
Yeah. Yeah, I mean the polarization arises because when the decoupling it's not instantaneous. So at that time if there's a quadrupole, generate a polarization signal out of it, and the signal also leads to higher multiple.
See, and this gravitational waves are causing the shear which the matter distribution cannot cause. Is it related to the bending of gravitational waves which we keep hearing? Or
Yeah, if you have a bundle of light coming so that of light, if it's a circular bundle, it gets into an ellipse. And it does exactly what people show you for the LIGO thing. It goes to this ellipse and
Lissajous figures kind of.
But that only gravitational waves can do. But on cosmological scales, you don't have ellipses dancing. So one has turned into this ellipse and frozen because the time. But we will see that effect.
Thank you.
Sir, I wanted to know what makes this a gravitational wave detector when compared to LIGO.
Oh, I mean, LIGO, it was enormous. I've spent time looking for a site for it. So that's enormous. But basically a 43 billion light year thing, right? I'm looking at distortion of light coming. I mean, I'm not doing Michelson interferometry, but all I'm measuring is a surface emitting light here, a surface emitting. and I'm seeing whether there is a distortion, right? So this is the same story as if I had my LIGO detector at all angles, and I was looking at a distortion of the circle, because there'll be mirrors at every point. Then so it's the same thing but on a sphere. So it's a 3D version of it. To me, they are the same. I mean, you're basically measuring light propagation from two different directions and comparing them. So in that sense, but the cosmic, because 43 billion light years is a cosmological scale.
We expect like the classical gravitational waves also to be detected.
Not at those scales. Okay, so at those scales, this is only one we know of. Okay, there are gravitational waves detected. I mean, phase transitions in the universe. Again, there are better experts, quark, gluon, plasma. If they are of a certain kind, they would leave some signatures in gravitational wave background that are at higher frequency relative to this, but they are much lower frequency relative to. So there are, at best nanohertz, but even lower than nanohertz.
Yeah. Can you pass the mic?
You mentioned about gravitational wave coming from the origin.
Yeah, I mean, origin of the universe.
Yeah. So, I mean, that would be that transverse like wave. But the CMB, we talk about polarization light. So, I was a little bit confused about this.
So they are transverse waves, but they are generated everywhere. So if plasma surface which is surrounding us, okay, it's hit by a gravitational wave. Compared to LIGO sees a strain of 10 to a minus 22. This is 10 to a minus 8, maybe at the weakest. So these things, and the time period is so large that it basically creates a, and the change in or distortion will take a Hubble time. I mean, tens of billions of years for that to change. The CMB actually evolves on cosmological scales. So in fact, there's a very nice undergraduate one had done under Lyman Page to ask if we had sensitivity and experiment 100 years later, would we detect these changes that come just because of the evolution of the universe? And you do find that it may be detectable in 100 years, but was that your question or something?
Yeah, I was wondering like one is transverse like wave,
Yes,
but other is the
gravitational waves are also transverse.
Yeah, but when we talk about CMB, that is a EM wave.
Yeah, so that's also transverse.
Oh, yeah, okay.
Yeah, so but it's not really the issue. I mean, transverse thing is only this polarization. There are no polarization projections at you. It's always a planar thing. The point is so you have, imagine sticks lining up a thing, and the question is, I have a, say, membrane with sticks drawn. Now, if I wanted to create a curl kind of a thing, I have to do something like a shear. I can't do it by stretching or,
Yeah.
Yeah, this is just for curiosity. So, is there any other competing experiments which are looking for this is inflation era?
I wish that was the case, because I personally in 2005, before I got into the LIGO game, I was also exploring the possibility of CMB experiment in India, thinking of doing now, even then. But at that point, the experiment field was so rapidly moving that it was clear that we won't have a role to play. I mean, we will have something on timescales where everything will be done. So I very much expect that by now we would have had launched another satellite. It so happens that ESA individually, no agency can do that, technically as well as financially. So they are looking for partners, and I feel that given the ability that India has and the economy being better, I mean, I don't know whether you're Kiran Kumar's. But the question is, what do you do with it? Now, if we have that thing, we should now go for the next big prize, right?
So this is completely indigenous project, this one.
No, this won't be indigenous. Partners from everywhere.
Okay, okay.
There's
So what is the timeline?
No, but that would be true for anyone. But in India, maybe it will be more so. But on 15-year time scale, that is the thing we are trying to do. We are developing there. A lot of it can be done. And if we have a ground telescope, then doing that, we will create people with the expertise to do the space.
So for this project, is there a
15 years.
Okay, okay, thank you.
Yeah. So that is the roadmap.
Why you want the satellite to be set up 2 point only, second Lagrange only?
Okay, again, second Lagrange points are stable points.
Yeah.
You want this thing to be cold, so you don't want to go close on the Earth, around the Earth, right? But then there are a lot of problems. Kobe had this problem of, the magnetic modulates the switches and things like that. Lagrange point is where Planck measured. James Webb telescope is there because it is far away from Earth. It doesn't get contaminated by anything emitted by Earth. It's a very pristine place. It's also semi-stable, so you don't just loop around the thing. And it is a place where you can maintain. You have millikelvin detectors, and at some level the ambient does affect it at a tiny bit. But Planck has shown us that over 3-4 its detectors temperature variation was very, very minimal. Okay, there were no, so it's a very stable platform to measure it from. So Lagrange point. Yeah, L2 is the one which looks away from the moon. The configuration, L1 is the one closer to sun by not much actually. So people, when Aditya was launched, people kept saying we are staring. It's only 3% of the distance lesser distance, but it's still better because nothing is in between. In this case, we want to look away from our Earth-Sun system. So Lagrange further away is L2. Now they are Lagrange along our orbit. LISA will be using them. This gravitational LISA, you can check it out. It's okay. So there, different user systems we have. I mean, these special places we have.
Sir, yeah. So
Okay.
when we're using Planck data, either there's two options, right? There's in the archive there's either polarized data or the polarization removed data in your Planck archive.
Polarization removed data.
Yeah.
Or the polarization. Are you talking parameters?
No. The Planck archive.
We have the intensity measurements.
Right.
It's not polarization removed. Basically, polarizations are added up. The intensity measurement is this polarization square plus that polarization square root.
Right. Will we? In these two data sets, in the difference, like the difference between these two data sets, notice the gravitational waves with the differences in these two datas?
No, not. The intensity has nothing to do with gravitational waves, fluctuations,
Okay.
right? So you have these two polarization, and the square of them is what you call intensity.
Right.
So they are not really independent. Square these two maps and add them. Okay. Technically, in principle, there's no. Okay. And then, if when you have this pattern of stakes, right? Because it says with maximum, and that I don't see what you can subtract out and measure, but we are already thing. We are never measuring the absolute value. We are comparing measurement here to the measurement there, right? All through every CMB experiment is a differential measurement.
Right. So, I mean, when we're comparing, so, I mean, if when you have an imprint of your gravitational wave in the CMB, is it just because Planck isn't at a and that we're not able to observe it, or
sensitivity.
Okay.
It's a sensitivity issue, and also Planck was kind of proposed at the same WMAP.
Mhm.
And the biggest questions then were just to see these fluctuations better, intensity fluctuations. People were not hung up on polarization. While Planck was being built, polarization was detected. It was retrofitted into the Planck design because CMB experiments take a long time. So, Planck was proposed in the 90s, mid 90s, the same time as WMAP, and flew in 2009. Right? So, you shouldn't be shocked. I mean, that is James Webb took decades, right? So, that's how the challenge is. But you have to start. I mean, you can't wait for 15 years and then start.